few things that affect reaction rates. We're going to talk about activation energy, which is one of them, mechanisms, and catalysts. So let's go ahead and do that. So the rate of collisions between the reactants, obviously that's going to be affected by temperature. The faster motion is going to happen and more collisions are going to happen with a higher temperature. That's just common sense, hopefully. Some of the collisions, depending on how they have to be oriented, not all collisions will have the right orientation, and so they may not produce a reaction because they won't be oriented correctly. And then some of them won't have sufficient energy to actually make the product. So they have to collide with enough energy. So when I increase temperature, I'm going to increase the rate of the collisions, and then I'm also going to be increasing the number of collisions that have enough energy. So temperature definitely goes into this, which is why K, the reaction, the rate constant, increases with increased temperature. All right. So if I increase concentration, if I add more reactants to a system, then yes, of course, I'm going to make more products. And so that will speed it up as well. Surface area. So this is on the AP exam. They might have, you need some iron. Well, if it's a sheet of iron, like metal, or mesh pieces that have been ground up, obviously the ground up pieces will have more surface area. That's good old like 5th grade science, right? When you increase surface area, things go a little bit faster. Are you feeling me okay on that? Okay. And then temperature. So this has to do with collision orientation. And so if I have NO2Cl and it must collide with another particle to make nitrogen dioxide and chlorine gas, if it collides such that the chlorines are not going to be in contact with each other, it's not going to be able to make this temporary, what's called an activated complex, where they're stuck together for a second before they break apart. So these would come together and form like a large, very temporary molecule, and then they would break into their components. And so it has to collide with the correct orientation, right? So if you took your shoe off, because I told you to, so if your shoe is, part of the reaction, and so is your foot, right? If your foot collides with the shoe like this, you don't make a shoe foot, right? So you have to collide correctly. We're coming back to the shoe. That wasn't the only reason I got you to take your shoe off. All right, so when you're looking at these graphs, they're reaction pathways, okay? And so they show you what's happening with energy in a system during a reaction. Before you even decide anything, you need to look at one thing first, because it's what people mess up every time. You need to look at the amount of energy in the system or in the reactants when you start, and the amount of energy in the products. If it's lower, then energy left is exothermic. Okay, that's later in the PowerPoint, but that is the first and most important thing to look at, because what will happen is some of these graphs have like 4 or 5 different little intermediates or elementary steps, and so you kind of get lost. But this is exothermic because the energy decreased. Now, the amount of energy that is needed to be added to the system to make that activated complex, that temporary where everything's stuck together kind of situation, that's the activation energy. Okay? And the change in energy during the reaction is that change between the reactants and the products. So you kind of have to, when you're looking at activation energy, it's very common to think this whole thing down to the 0 on the y-axis is activation energy, but that's not right. You have to be really careful about that. Activation energy is just going to be between the activated complex and where you started. You see that? So these are just some common tricks that you need to look for. The enthalpy of the reaction will just be the change from where you started to where you end, and it doesn't matter about how tall this part is. How you feel? Okay? All right, so anyway, if the collisions have enough energy, then, so what's happening here, like if I have these little blocks, this would be AB, this is C, so they would collide, what does it make me see? So they would collide like this, so follow me, this is where you start, and then if they collide with enough energy, they would overcome the activation energy. So in the middle, they're at this, what's called activated complex, before they break off, and then here's my products. So that's what's happening here. Notice too that energy is needed to break bonds, and then energy is released as new bonds are formed. So releases energy. And so you'll always see this up and this down. But the trick is sometimes the energy released when new bonds are made is actually less than the energy needed to break the bonds in the first place. And so this would be an endothermic reaction. More energy went into it than actually came out. And that's kind of where it starts coming all together. Isn't that fun? How do you feel? You get it? But it's just running off, right? Okay, fair enough. We're in this together, my friends. All right, so moving on. If enough energy does not go into the particles as they collide, they will not overcome the activation energy, and no reaction will actually occur. So it will just we'll be left again with just the reactants. Not enough energy will be there to overcome the activation energy, so we actually won't form that activated complex, that temporary stuck together kind of mess. All right, so going back to things we already learned, here's a Maxwell-Boltzmann distribution. And if you look in Unit 2, where I actually put the Maxwell-Boltzmann distribution, like in Schoology, it has this EA. And so this EA right here, that's activation energy. E sub A is energy of activation. Now, here's where this ties in. If I look, when I start to heat up these particles, if you recall, if these are gaseous particles, and I draw in some particles at different temperatures, and then we add in those vectors for how fast they're moving, those vector arrows. Y'all look like, please stop, please stop, please stop. This one's going about this fast, faster, 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 and faster, right? And so I see that with the higher temperature, more particles, a larger percentage of the particles are moving with this faster speed. So they're going to collide with enough energy and more frequently because of higher temperature. Now, where this comes in graphically is, if you look at this green curve at this higher temperature, there's the fraction of the particles that have enough energy to overcome the activation energy to get to the top of that little peak. Right? At that lower temperature, at that purple graph here, now we can see that the portion of the particles at that lower temperature that have enough energy to overcome the activation energy is less. So that's where that ties in. Do you see it? Okay. You sure? You just didn't want to, right? But please stop, Miss Maria. Please stop. I'm sorry. I'm making you successful human beings. How to read graphs. All right, we don't need to know that. If we don't need to know it, I'm not talking about it because we got enough to know, right? Okay, so anyway, when we're looking at these reaction pathways, these little graphs with the little roller coasters, okay, the higher the activation energy. Now, make sure again you're only reading it from where you start, not from the x-axis, not from 0, but from where you start. The higher the peak there, the slower the reaction is going to take place. Versus this one will go at a faster rate. Now look at it here. If we go back to the Maxwell-Boltzmann distribution, see how this is the lower activation energy? That would mean that second graph that had a shorter peak, the activation energy would be somewhere right here, and then I'd have a larger portion of the molecules that have enough energy to overcome the activation energy. See how those tie together? Are you sure? Did you draw it? Thing, are you okay? Yeah, you just don't want to be okay. Just want to stop. Sorry, you got 33 more days, man. Please make it stop. So again, the graph, the line on the graph that I just drew in, where the activation energy is less, that would be this one. So the reaction will happen faster because more particles, higher concentration of particles, would have enough energy to overcome the activation energy. So in summary, they have to collide. The collision must have the right orientation, and the energy of the collision has to be greater than or equal to the energy, the activation energy. Yes, it can be equal to. All right, so this is what I had already told y'all. Exothermic means you end up with less energy in the system than you started, so energy has been released. Again, activation energy is only from where you start, not from the axis down here. Be careful. And notice here, the activation energy again is from where I start to the peak of the graph, and then I can see that the enthalpy of the reaction, or the energy change of the reaction, is actually a positive or a gain in energy, so that endothermic energy has to go into the system. Okay. Okay. So, in summary, I feel like I already said that. Okay, now tomorrow we do more math. It's a little worse. Turns out that most chemical reactions are reversible, which means they can, the products can actually make reactants. So if I took this a second ago and I had said, AB plus C gives me this, that also means that, the opposite can happen. And they're kind of going back and forth. And that's fun, right? So look, here's the deal. The reaction pathway for reactants making products looks like this. And that has pretty low activation energy in comparison to, like, if it goes the opposite way, right? If it goes the opposite way, now I see that the activation energy here, the enthalpy overall here is actually, I'm still reading it the same way. Sorry. They flipped the graph, and I kept reading it the right way. But now I see the activation energy is actually greater, and it actually needed energy to go this way. So, which way would probably happen in this reaction if it's reversible? Probably the forward reaction would be favored, right? See? I'll catch you tomorrow on that. I'll probably come back to this after you understand what I'm talking about. Fun times. I'm real excited about it. You don't need to know this. You don't really need to know this either. The Arrhenius equation, if you are one of those people that might get a 5 and you're going to study medicine or chemistry, they will have expected you to at least seen or heard about the Arrhenius equation. This is also on the chemistry Olympiad exam quite a bit. The chemistry Olympiad exam doesn't give but like 3 equations, and this is one that doesn't have any of that other stuff. But anyway, you remember our friend K, the rate constant, that little letter in front of the brackets? It's fine. Everything's cool. The larger the K value, the faster the reaction goes, right? Where's my thing? And the reason the larger K yields a larger rate is because rate is equal to K times some stuff. So K's bigger, then the rate gets bigger. Yeah, that's fun. Okay, so why this K is not some magic number that you get when you just plug numbers into a formula. It actually has some things that affect it. So activation energy, right? So if the activation energy is less, that's going to speed up the reaction. R is just thrown in there. The temperature is obviously going to affect it. The higher the temperature, higher the rate constant. And then the constant A, the capital A right here, is, so this is basically A and then E to the power of all this. You don't need to do this, but if you want to, in a minute you can choose to do that. But this A right here, it's related to how frequently and the orientation of the collisions. So if it's basically how likely is it that the collision would make a product. Okay? So if you want to do this, the magic of the Arrhenius equation, if you end up, you know how natural log and E are kind of like the inverse operations. If you take the natural log of both sides, you can end up graphically being able to say that the slope is equal to the negative activation energy divided by R. And so you can use a graph to solve for activation energy. That's completely optional, but that's how it works, okay? Moving on to things that you need to know. Now this is where everybody comes back together. Okay, so most reactions don't happen in one step. So honors chemistry and chemistry up to this point for you, you've been seeing the overall reaction, except for that time that we had done Hess's law and then we had combined the reactions, and you know how they, like if you had a match, you could take them out. Do you remember that? That's always a thing. So if you see one thing on the reactant side and the same thing on the product side, it's not, and if it cancels, it's not going to be written in the overall reaction. So before I even talk about anything about kinetics, going back to what you already know, you can see that N2O2 is a product and a reactant. There's one of each, so that's going to cancel, and then I'm not going to have it in my overall reaction. So before I even teach anything, do you understand that? You good? All right, so what's happening here is this process actually happens in 2 steps. The individual steps are called elementary steps, and the first elementary step right here creates N2O2, and then that N2O2 combines with oxygen to make nitrogen dioxide. Now this is actually an intermediate, okay? An intermediate pops up in the middle and gets consumed during the reaction. So intermediates won't be there at the beginning. So it's not here, this is the beginning. This is step 1, makes that, this is step 2, and that's what you end up with. can use them to write the rate law. So let me move on to that part. Okay, so like I had said, the intermediates are produced and consumed during the reaction. They're not there to start with, so that's the difference between it and a catalyst, and I have a way to remember catalyst in a second. Good so far? That's what a intermediate is. Alright, now, remember that for the overall reaction, so this overall reaction right here, I cannot say that the rate is equal to, and remember, we're just looking at reactants. I keep saying that because tomorrow we're going to do products too. So I'll keep saying that on purpose. But I cannot just be like, okay, I got a 1 in front of that and a 1 in front of that. You can't do that. That's not a thing. You can't write the rate law from the Bounce equation. But you can write the rate law from the slowest elementary step. So if they give you a bunch of steps, 2, 3, 4, however many, and it's going to tell you this one is the rate determinant step, RDS, or to say it's the slow step. You can write the rate law from that using the coefficients of that little equation. Isn't that fun? That's the only time you can do it. So let's go ahead and check this out. So, experimentally determined that the rate law for this reaction was K times the concentration of nitrogen dioxide in its second order. So this was experimentally determined. Let's look at the elementary steps, okay, and see how that works out. So, do you see how NO2 and then that 2 is squared there? That's the rate law. The reactants raised to the power of their coefficients is the rate law. But look here. If I take the reactants in this second elementary step, is that the rate law that they already gave me? No. The rate law that they already gave me is this. So what the question will do is they'll say the rate law was experimentally determined to be this mess. Alright? And then they'll give you 2 elementary steps. Whichever one's reactants raised to the power of their coefficient matches what they gave you, that's the one you know is the slow elementary step or the rate determinant step. So I know this is the slow elementary step or the rate determinant step. And if you know the rate determinant step, if they say beside of it slow or rate determinant step, then you can at the same time say, okay, the rate is equal to K NO2 squared. That's the only time with kinetics that you can use a little equation that is raised to the power. That's the only time you have a series of elementary steps. Okay? So I can tell, again, this is the step 2 is the fast step. Step 1 is the rate determinant step. Now, let's connect this to what I already told you about graphs, because you know graphs are real fun. So I'm going to draw a little graph in here. If I draw the reaction pathway for this, I'm going to have 2 steps. So I'm just going to start somewhere. I don't know if this is endothermic or exothermic. It doesn't matter. The first step, though, is slow. You follow me so far? So that means it has the highest activation energy. And the second step has a lower activation energy. And that's what the reaction pathway for this would look like. And that's the kind of question they're going to ask you. So you figure out step 1 is the rate determinant step, or they tell you it's the rate determinant step. It has a higher activation energy. That's why it's slower. You got to get over a bigger roller coaster hill. You see? If I had 3 elementary steps, which sometimes you do, and if the third one was also fast, then it would just look like this. However many elementary steps, how many little camel humps you got? Sorry, I just can't make it any easier. That's the best I got. And then I said, like I said already, the activation energy for this is this much. Not all the way to the bottom, but that much, okay? And you can see here the activation energy is less and less. You good? How you feeling? Okay, let's keep going with that. So, if it tells me that this, is this the same thing we're just doing? Yeah. So I think it's just going over it one more time. Again, this is a intermediate, and then the rate is equal to that raised to its coefficient. No problems there. I already explained that. What is this doing? Okay. This is not necessary. I don't even know. No. Were you following me when I was explaining it? No. Okay, so determine the rate law. It has to be done through experimentation, and so through the experimentation, they'll figure out what the elementary steps are, and then the rate law will tell them which one's the slow one. You don't have to know that. Don't let this freak you out. It's not a big deal. Unimolecular things, just start with one thing. If I have two, whatever. No worries. The thing that we already had talked about that is important, though, this one's first order because it's 1, and then second order, 1, 2 is second order, third order, right? The only thing that, you followed me on that on the other day, right? The only deal is, the more reactants you have coming in there, that means that you're going to have 3 things colliding in correct orientation to make the products. So these are going to be, they're going to have a lower K, right? Because they're not going to go as fast because they're all going to have to collide in the correct orientation. The lower the molecularity, the higher the K, or the easier it is for that reaction to happen. Why are y'all laughing? This sounds terrible, but yeah. Do you follow me though? Yeah. It's probability. Yes, sir. I'm about to do that. I'm not done yet. I got you. All right, so go ahead and talk to your neighbors. The rate constants here are associated with the slowest elementary step. Which process has a higher rate under standard conditions? So talk to your neighbors, and I'll pick somebody. Yeah. Oh, well, intermediates are formed and consumed during the reaction. Catalysts come in and leave the reaction. Now, I'm not the catalyst, so you're okay. Which one's going faster? Yeah. Y'all little faces are so sad. All right, so I'm not gonna do it to you again, Abby. Grace. Yeah. Why?
Because the rate constant is lower. I'm trying to word it because I keep mixing them up. But basically the slope is going to be steeper.
Yeah, because the slope is equal to K. Now, what happened in first period or second period is the same thing that just happened now. And you fixed yours, so you said it right. But on scientific notation, if you're not real super good at that, depends on if you had H or not, I guess. And that's what happened in second period, to be honest with you. This is 0.00015. This is 0.00027. This number is bigger than the second number, so its rate constant is larger, which would mean that the rate is going to be larger because it gets multiplied again. So, anyway, -4 is bigger than -6. Okay. No child left behind. We're going to catch all of you up to all of your things that you ever learned in your life, like pretty much, right? Like that's what we're doing in here. So process 1 is faster because if you had, here's the deal. These are elementary steps. So this is second order and this is second order because this has a coefficient of 1 and this has a coefficient of 1. Yeah. Okay, so the rate laws are going to be the same for them, and so the only difference is going to be the K. Do you follow me on that? The rate law for this one would be rate. Okay. The rate law on either one of these is going to be rate is equal to K times the concentration of A and B, or C and D. So if they start with the same molarities of 1 and 1, then rate is just going to be different because of the K. Moves on, cries a little bit. So here's another question. The rate law is associated with the slowest elementary steps. So still here, these are the slowest elementary steps. Which process is likely to proceed at a higher rate under standard conditions? So think about the molecularity. Chase. Think about how many things are having to collide with each other. it would probably help you to think backwards. If this is the slowest elementary step, then you can actually write the elementary step reactants from these, and I'll do that in a second if you need. I love y'all's facial expressions. I'll give you a second to talk and I'll pick somebody. What is it so funny? Batteries. Redox reactions a little bit more, and some of them was thermodynamic favorability. That part's hard. I got y'all. There's nothing I can't explain. There's nothing you can't learn.
Yeah, that's the problem I've had in college. We learn all of these. We learn all of these formulas, like, but what I always have a hard time with is learning when to apply them to which situation.
Yeah.
Like when, like looking at a question and reading it, like what do I apply to this?
That's just, I have some formulas. Like, you just have to dive in, you know? You got the answer yet? We are going to review this content 2 more complete times next semester for the ones that decide. That doesn't make it. That doesn't make it better, does it? That doesn't make it feel better. But you'll get it. Amanda, which one is going to proceed at a higher rate? Why? That's not necessarily the answer. Activation energy is that's going to depend on K and But the thing is, here's the deal, y'all. If these are the slowest elementary steps, if I go to write the reactants for the slow first element, this one, process 1, it's going to be 2A plus B. So I have 3 particles that must collide correctly. The slowest elementary step for the second one is just C plus D. So that means only 2 blocks have to hit each other, right? Versus 3 blocks. Yeah? So the probability of that occurring is higher. So the fastest one is, you're right, it is going to be process 2. And it would probably have a lower activation energy. But like what? So you're right, but I just wanted to expound on that a little bit. Just a little bit. We're almost sort of done with this. Catalysis. Did I go into, I want to make sure, did I skip the one where there was, I feel like I did skip something. Did I skip the one with the intermediate, Christian? I did skip it. Okay. I'm sorry. Alright, I did skip it. I need to go back to this. I thought it was the same slide because it looked like the same slide, and it's not. Alright, so the intermediates. Are y'all okay with the fact that this is the intermediate? Well, let me tell you a little secret. When you write the rate law, it can't have anything in it that's not in the overall reaction. Is NO3 in the overall reaction? No. So what you have to do, it's not that bad. What you have to do, this is the slow step. So I know that my rate law is NO3 and NO2. Are you okay with that? But can it have NO3? No. So where did NO3 come from? What you have to do is just go backwards and substitute in where NO3 came from. So let's do that. NO3 is here, and it came from, I'll just mark it out. Okay? It came from another NO and an O2. So my rate law for this would just be rate is equal to K, and then NO2 squared, or excuse me, NO squared, and then O2. I ran out of room. That's all you gotta do. You just find where it came from and write it down. Got 2 of them squared. I don't know. But this worked. Listen, look at me. This worked. far as getting fractional order, sometimes that comes out and sometimes that happens like in your textbook, but we don't have to do that. So anyway, they do all that and they get the same thing. No. I'm sorry, I skipped that. I didn't mean to. Okay, so catalysts. Catalysts are like Cadillacs. Okay? I'm just trying to help you out here. So let's say we're going on a road trip to, I don't know, we're gonna get in our car, we're gonna go to the Grand Canyon. It's gonna be awesome. Okay? Certainly you think that your Cadillac will get you there faster, yeah? Now, do you get in your car at the beginning of the road trip? Yes. And do you get out of it at the end? Yes. So catalysts here at the beginning and the end of a reaction when you have your elementary steps. They do form an intermediate, but they're not consumed. Like your car isn't consumed in the road trip, right? You just get in and out. What they do is they provide an alternate pathway. And this is the part of the definition of catalyst that everybody leaves out. Yeah, they lower the activation energy, but they do so by providing an alternate reaction pathway. So it means that little graph that we had drawn with the little roller coasters, it makes a new roller coaster graph, okay? And so I'm going to show you how that works. Does everybody see the roller coaster graph in their mind?
I see camels.
Good. You having what is that called? A mirage? Is that a thing? What in the desert? Do you see camels? See the fun? He said he sees camels. That's funny. All right, so back to AP Environmental Science. I feel like we talked about AP Environmental Science once. Did that happen already? Whatever. All right, so here's the deal. If I want to break down, I don't want to, but if ozone in the atmosphere is going to get broken down, here's the overall reaction. O3 plus oxygen gives me 2 O2s. Now let's talk about how that works. Okay. First of all, do you see an intermediate? You see it? So intermediates are created and then consumed during the reaction. How do you feel so far? You should already know that. Now, if you see something at the beginning, excuse me while I draw a Cadillac. You know what? And it's at the end. That's a catalyst. Like a little Cadillac. Whatever. Now, go with me, y'all. If this is the overall reaction, okay, I'm going to draw the reaction here. The overall reaction is this. If I draw the reaction pathway for that, the little energy graph, that's one step, yeah? So, it has a really high activation energy. It's probably endothermic. So, I get it, because it takes energy from the sun. Remember? Yay! Why does it have a high activation energy? I don't know the number, but I know that it's higher than the without the catalyst. It's higher when you don't have the catalyst. So let me show you what happens with the catalyst. How many of these little camel humps am I about to have to draw? 2. Do you know why? There's 2 elementary steps. How do you feel? You good? All right. So with the catalyst, what's going to happen? I'm still going to start same place. I mean, you know, as far as the energy in the system, but I'm going to, instead of having that big activation energy, the first elementary step may be here, and the second one may be here. And so the elementary steps have lower activation energy, and if I go back to that temperature graph for Maxwell-Boltzmann, I'm going to have more particles that have enough energy to make this activated complex into the products. That's what I'm talking about when I talk about a catalyst. It provides an alternate reaction pathway that has lower activation energy, even though it may have more steps. Get it? You don't get it? You got a question?
So does the second graph come from the first one?
No, this second graph, this part right here would be this part. And this part right here would be this part. And then overall, look over me. Overall, you start and you end at the same place. It's here. But you just have, instead of one step, you have 2, and then each of those activation energies are less. Are you okay? Do you get it? It could be worse. I could not talk about camels and stuff. I mean, it could be worse. She said, I know what a camel is. Alright, so I drew my own reaction pathway because this is wrong. Their little reaction pathway is wrong. You know why? Because it only has one elementary step. It should have two. So this should have two humps. I was right. And the AP exam asks a lot of questions. They'll give you these elementary steps and they'll be like, which graph matches that? And you got to be able to say, well, there's two elementary steps, two camel humps, okay? Being sad about life, yeah. Okay. So anyway, it provides another reaction mechanism or pathway that has a lower activation energy. Equilibrium, we'll get to that tomorrow. As far as acid-base catalysts, we don't need to know about this right now. Alright, surface catalyst. So you got your shoe off still, right? Take your shoe off and just grab it by a shoestring and look in there. Got it? Or not. Who's doing it with me? Cool. Alright, so what I want you to do is we're trying to make a product, and a product is a tied shoe. Okay, so I'd like you to tie your shoe in the air. Yeah. In the air like you just don't care. Do the things. I did it. Cool, right? So that was fun. You're not on in the air. Just like you don't care. What did you say? I can't help some of y'all. Alright, so if your shoe is dangling and moving around the air just like some gas particles, and they're trying to collide to make a product, that is going to not happen very frequently. We had talked about how gases, we had talked about how gases, don't really interact with each other. They don't have any attraction to each other. They're very separated, blah, 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 right? Well, if I have gases and then I have a surface catalyst, what can happen is they adhere, there's some adhesion here between, and this is actually called adsorption. So they're adsorbed to the surface of the metal. So now, instead of dangling your shoe in the air, put your shoe on the table and tie it. I don't care. Is that easier? Yes, because what's happening is the surface of the table is holding your shoe for you so that you can allow the strings to be maneuvered in the appropriate way. So what happens with a surface catalyst is the surface of the metal, in this case, holds the gas particles on it. They're held there, and then bonds can be broken and new bonds can be formed easier. Just like you tying your shoe in the air versus tying it on the table. That's the surface. The surface catalyst. Y'all remember in AP Environmental Science we had talked about catalytic converters and how people steal your catalytic converter because it's got platinum and palladium in it? That is a surface catalyst. The carbon dioxide molecules stick to those surfaces of those metals and they react with oxygen to make carbon dioxide. That's how that works. Catalytic converters, let's say it again, catalytic converters convert carbon monoxide to carbon dioxide, and they're surface catalysts. And this would be an example of a heterogeneous catalyst where there's different phases of matter, gas and solid. Y'all know y'all thought that before today, did you? I told you it was bad. All right, so anyway, on this surface that is easier to happen, this process is easier to happen, and so then it can be desorbed. So adsorption is where it sticks, and then desorption goes out. You don't really need to know that, but it's good times. Enzymes act as catalysts, and so when we talked about, when you talked about, hopefully, in biology, how enzymes work, there's like this, there's an active site where it's like a puzzle piece and it fits in there, and so it's like held there until the bonds break, and then that reduces the activation energy. So the substrate is what it's called. Whatever. Done. So I'm gonna let you guys take the answer key. Let me stop the video.